That was the signal.
So we can start. So we have lunch with Mark from Amazon today. He was telling that he was just asked to introduce the public lecture speaker, Stephen Schenker, just a few minutes before the lecture started, and we all admiring how well he did and laughing. Without knowing what's going to happen to you when you are trying to walk into a colloquium room. That I'm supposed to introduce the speaker. And today's speaker is Ahmed. He is interested in understanding the connection between quantum information theory and quantum gravity theory. And he has amazing set of achievements, even when he was a graduate student, I believe, in Santa Barbara. He formulated what is now called black hole firewall paradox, which is we are still puzzling about. We had lots of talk about that already. And then when he was, I believe, a postdoc at Stanford, maybe even a postdoc in IAS, he did a very impressive work to recast the CFT correspondence in the language of quantum error correcting code. This one, particularly, thank you for doing that because I was able to use that particular work to prove that quantum gravity has no global symmetry, for example. So this has also very important. And then just before the pandemic started, he wrote a very influential paper on the resolution of the puzzle about the von Neumann entropy of Hawking radiation, and he might mention some of those today's talk. He was at the University of Toronto and went on to UC Santa Barbara to have a PhD, and his advisor, I believe, was Joe Kortinsky, who unfortunately became ill and passed away a few years after he got his PhD. Recently, Ahmed and his friends edited the autobiography, Joe's autobiography, which was just published by MIT Press, called Memories of Theoretical Physics. It's a wonderful book that I recommend to you. And after that, he became a postdoc at Stanford, I mentioned, and was a long-term member at the Institute for Advanced Study. And now he's an assistant professor at NYU Abu Dhabi. He has received already many awards and honors, including 2021 New Horizons Prize in Physics, Fundamental Physics Prize Foundation. This winter, he was also here for one of the winter conference and gave, he was at the Physics Cafe, and he really gave wonderful public presentation at the cafe. So he is a great scientist and a wonderful speaker. So we are now in for a great treat. So here is Ahmed.
Thank you, Hiroshi, for that introduction. And thanks everyone for listening to my talk. So I'm going to talk about the central dogma of black holes. For the past 100 years or so, physicists have sort of had a love-hate relationship with black holes. Famously, Einstein didn't believe them right after Schwarzschild found his famous solution. And it wasn't until maybe the 50s or 60s that we started taking black holes more seriously. But when that happened, physics ended up being physics of everything and physics of black holes. Black holes were sort of an outlier. People thought that they didn't follow usual rules of physics. But in the past few decades, by following sort of the crumb trail, we've been finding more and more evidence that black holes are actually not so different from normal quantum mechanical systems. And that belief, if you will, goes under the name of the central dogma of black holes. Obviously, I call it the dogma here, but we don't need to be too religious about this. But let me explain what I mean by the central dogma. For that, you should all turn to the Book of Juan, where the statement of the dogma is that, as seen from the outside, a black hole behaves like a standard quantum system with a number of degrees of freedom that go as the area of the horizon divided by 4g Newton, and the system evolves unitarily under time evolution. More practically speaking, the statement is the following. But if you put a black hole in a box and you interact the black hole from the outside, you cut some holes out of the box and you allow to send and receive signals to the black hole, the claim is that you won't be able to tell if box contains a black hole or a quantum system with the following properties. First, is that it has a large, finite number of degrees of freedom. As I said previously, goes as the area of the horizon of the black hole divided by 4G Newton. The second, that it evolves under a Hermitian Hamiltonian that is chaotic in some sense and involves all-to-all interactions that couple a few degrees of freedom at a time. To begin, let me explain what a black hole is. So there's a quick recap. We know that Einstein's theory of general relativity says that if a star collapses, it can warp space-time sufficiently to form what is called an event horizon. And event horizon, which is sort of the point of no return. And what really happens is that as you squash the matter sufficiently, you trigger a collapse of a region of space-time that just crunches into itself and just it stretches and squeezes everything in that region, and which fuels more stretching and squeezing up until the space-time in that region stops making sense, and that's the black hole singularity. So even though the picture on the left shows that the singularity is in the center, it's not really in the center in the terms of sort of polar coordinates. It's really an end of the space-time to the future. On the right, there's a same picture of a black hole, but in so-called well, this diagram is called a Penrose diagram, where light rays go at 45 degrees. So here, singularity is given by this red hashed line or red line, this red region here is the collapsing star. Dotted line, is the event horizon. And I've drawn here two allowed space-time paths, one of which gets stuck behind the black hole horizon, because an allowed space-time path has to stay within the light cone, and a path that is allowed to escape the black hole's gravitational pull. And I guess I should have said time goes upwards. And the statement of the inevitability of black holes in Einstein's theory of general relativity, obviously one got Roger Penrose the Nobel Prize 2020. Well, I should say, if you have questions, please interrupt.
Inevitability in the sense that you go to a singularity once you cross the information. What is inevitability?
That if so without going to the technical statement, that if the space-time is collapsing in a certain way, there are sufficient conditions. If those are satisfied, it will necessarily collapse into a singularity, form an event horizon. Okay, actually, let me go a step back. So this is what black holes are. It's not clear how this object would satisfy all of the claims that I made previously. Some of the evidence started in the 70s when the two groups, Hawking, Bardeen and Carter, and also Bekenstein, realized that there's a connection between black holes and thermodynamics. This goes under the laws of black hole thermodynamics. First observation is that the area of the black hole, along with the energy or the total mass of the black hole, satisfy a first law of thermodynamics. dE is equal to dA times some number, which you could interpret as the temperature of the black hole. That number, kappa, is known as the surface gravity, is some property of the geometry at the event horizon of the black hole. Now, Bekenstein took this idea very seriously, and he said that you should really think of the area of the black hole as an entropy. If that's true, and the black hole is interacting with matter around it, and if it's behaved like a normal system, the total combined system should satisfy a second law of thermodynamics, or in this case, it's called a generalized second law of thermodynamics, where the quantity, the area of the horizon, plus the entropy of the matter outside has to increase under any process. That's a statement that under variations, for example, if lump of matter with some entropy falls into the horizon, then the increase of the area of the black hole has to be larger than the decrease of the matter entropy outside. So all of these observations solidified that you should assign the black hole an entropy, which is the area of the horizon divided by 4g Newton, now known as the Bekenstein-Hawking entropy.
There's also a third law, which we know in thermodynamics.
The third law would say that entropy is zero at zero temperature. There are various examples of black holes that actually have a finite entropy at zero temperature.
The models.
There are models of that, but it often depends on whether you have supersymmetry or not. So,
So third law can be violated by the black hole.
correct. There are definitely examples of black holes and supersymmetric theories that violate that.
There's actually an analog of a different formulation of third law where you can't attain zero temperature in sort of a finite process. That does hold for black holes.
So I have a question on the previous slide. Increase in entropy. So the next. No, next. Yeah, so if I drop something into black hole, the area increases just because energy increase. So doesn't it put some limit on what entropy of the falling thing can be? Let's say I have a falling thing that has much bigger entropy than its energy.
Much bigger entropy than its energy.
Increase in area of black hole is just energy that goes in, not the entropy. No?
Well,
It's a mistake.
I think for any system, there's a maximum entropy that it can have, given its energy. So given those conditions being satisfied, so the thing you're dropping in is a reasonable system, and things should always follow.
So if I have something falling into a black hole that is extremely hot,
Yes.
okay, so then all that entropy will disappear.
The claim is that all of that hotness contribute to the area of the horizon.
I think the point is that that condition implies a condition about a condition that should hold in flat space, and it was recently argued using properties of quantum field theory, so relativistic quantum field theory, that condition indeed holds. There is a bound on the entropy as you were suggesting.
Good one.
On the Bekenstein bound, the Cassini-Bekenstein bound.
Any further questions? Okay. You can ask now, okay, this thing behaves like an entropy, but is it really an entropy? In seeing is clearly an elephant. Okay. The claim is that yes, because you can derive it in some sense. So let's talk about just thermodynamic entropy. So this definition, or you can think of it as a measure of the size of phase space of a system. It's defined in the following way. First, write down the partition function, z of beta, which is just a trace of e to the minus beta h. Beta is the inverse temperature. And you can extract from this the thermal entropy just by acting on it with this operation. The question that we're after is whether you get this formula, and what are these microstates that contribute to the entropy of a black hole? For a box of gas, we know it's all the different configurations of the particles. What is it for a black hole? Okay, so let's do this. So there's a lot on this slide, so let's go slow. We want to compute trace e to the minus beta h. But what this means is that you take your system. Let's imagine you have a regular nest matter system. Consider you just consider the system in front of you, and the way you compute trace e to the minus beta h is you you have your system, you tensor it across Euclidean time circle, that's e to the minus beta h of length beta, and you compute the partition function on that space. So it's your system cross time. The idea is that you should do the same thing for a black hole. You should look for a space-time, which is spatial metric of a black hole, tensor some Euclidean time direction. And so this is the setup of the problem. And given this setup or these boundary conditions, you have to solve Einstein's equations. Once you do that, you find the following solution for these boundary conditions. This is famously known as the Euclidean cigar. It's hollow, and the length of the circle is just beta. Point here is the tip of the cigar is nothing but where the event horizon of the black hole is. I sort of pulled a fast one on you. I considered for my metric of the black hole, I considered just the outside of the black hole, because I knew what the answer is going to be. Yes?
So in a condensed matter system, I know what beta is, it's the temperature. And usually you understand it as a bigger system, which may be in a pure state, and then your subsystem is entangled with it, and that gives you the temperature. Now, in the case of the black hole, is there a similar concept of what provides is it not an isolated black hole? It's in some environment?
So let me see. Let me give a few answers. So first, in a condensed matter system, usually you consider something like, perhaps this is not exactly what you're referring to, but let me just say it. Usually consider your system, usually introduce a copy of your system, and you consider the thermal field double state, those two systems. And when you trace out that copy, have a thermal density matrix of your system. I'm trying to do the same thing here. So this procedure of tracing out this other system, well, the density matrix, this thing is essentially the trace of that density matrix. So you should think about it. In a normal condensed matter system, you have the statement of having temperature beta or inverse temperature beta, the statement that you have this Euclidean symmetry along this direction of length beta. For a black hole, usually you impose that condition that the length of the circle is beta at infinity. There's some boundary condition on the solutions you're looking for. Okay, so that's one answer. Another answer is something, I'm sort of jumping the gun. The thing that the black hole is in equilibrium with, ultimately it's going to be some Hawking radiation coming in from infinity and being also emitted by the black hole. It's a black hole in a thermal bath radiation. Ultimately, that's what it's going to be.
I think, the follow-up on that question, temperature has to do with equilibration time. So in condensed matter, typically equilibration times are nothing. And you can talk about temperature on any time scale. Being in contact with Hawking radiation depends on the size of the box. So can that temperature be defined on some reasonable time scale that is much shorter than the lifetime of the black hole? That's the question.
Yes, I think so.
It can be.
Yes, especially in controlled situations where you put the black hole inside of an ADS spacetime, which is like a black hole in a box. And you can compute, say, correlation functions on that background. You perturb it, you see how long it takes to thermalize. It's all controlled by a parameter that I'm defining here, beta. Okay, so here, the takeaway here is to find a solution that corresponds, that comes from these boundary conditions of having this circle of length beta, and you plug it into your partition function. You know that the partition function you can express in terms of a path integral. We all learned that in kindergarten. And here we're looking at a particular solution. And so we're looking at a saddle point of the gravitational path integral evaluated on this space-time. Here I've sort of separated gravitational part, it's the matter part, we're not going to talk about immediately. Okay. So then you do this, you have that expression, you take the log of it, and you multiply it, you act onto this operation, and you get, boom, the area of the horizon divided by 4G Newton, which is nothing but the Bekenstein-Hawking entropy. If this doesn't shock you, maybe didn't deliver the message right. This was a single configuration. Nevertheless, it gave us this huge number, area over 4G Newton. Why? This is probably one of the deepest mysteries in the study of black holes. Why does one configuration in this Euclidean gravity theory use a number which is not one? Another sort of added surprise is that there's been a check of this number in specific models. For example, in string theory, where you can, for a certain kind of supersymmetric black holes, if you start with your theory with a black hole, and then you tune the coupling of the theory, you have this power. You have the power to do this in string theory, and you can make the coupling to be very, very small. What happens is that the description of the black hole becomes instead a description of something called E-branes string theory, where it's now essentially a bunch of copies of field theories in which it's easy to count different number of microstates and so on. So there are a number of microstates here that we understand. We count them and we get area over 4G Newton. It's one of the triumphs of string theory, but we don't understand why does gravity in the strong coupling regime know about this number, the weak coupling regime. Okay, that was the evidence for why you should believe that that number is really an entropy, the Bekenstein-Hawking entropy. But if so, you end up with a puzzle. So this is a thermodynamic puzzle. So suppose you compare a black hole in a box with a gas in a box. And you can consider the regime where at large volume, in this case, black hole becomes thermodynamically disfavored. Number of states of the black hole in the box is much less than the number of particles, the number of states of the gas in the box. So there must be a process that would take A, B. Classically, there isn't. Black holes are stable. Nothing can escape from the event horizon of a black hole. However, but there is a way quantum mechanically. That's Hawking radiation, which is this phenomenon where black holes emit radiation via pair creation at the horizon. So here's a picture of a black hole that's evaporating. At time steps of the temperature beta, let's say, a pair of particles is emitted from the vacuum near the horizon. Sorry, let me take a step back. Origin of these particles is something that familiar for quantum field theorists and also for condensed matter. At low energy states, you expect to have a high degree of entanglement, local entanglement. And here the statement is that in quantum field theory, that's true everywhere. Locally, if you condition the space-time, you'll find there's a lot of entanglement. The horizon of a black hole is not special in any way. It's just like any other region of space-time by the equivalence principle. There's a bunch of tangled pairs across the horizon. Now, something special that happens at the horizon that doesn't happen anywhere else, that pair of particles get separated. One half of them fall into the black hole. The other half escape the black hole and go out to infinity. Once they escape, they carry away with them energy from the black hole. So here, as a function of time, you start with a black hole, just by itself, it stops the star. And as a function of time, more and more Hawking modes get emitted until on the final slice, you're just left with Hawking radiation and no black hole. So this is how you would transition from the box containing the black hole to the box containing just radiation.
Is this an entropy conserving process or entropy increasing? process?
Increasing. Entropy increasing process.
There's more entropy than.
Correct. In the sense of thermal entropy, just the sense of coarse grained thermal entropy.
Log of the number of microstates.
Yes. Okay. What's something amazing about this result that this is the temperature that falls out of that calculation for the Hawking radiation coming out of a black hole. And this is the kind of formula that you sort of you don't expect to get until you sort of solve the theory of everything. It has all the fundamental constants in it. It has h bar for quantum mechanics, it has c for special relativity, it has k for Boltzmann's constant for statistical mechanics, Newton for general relativity, and circles. 5 for circles. Yes, 4. So it's really a beautiful formula. Okay. Next, I'm going to present a series of challenges that process of Hawking radiation gives to the so-called central dogma. I guess maybe one would call them heresies. Okay. The challenge number 1 is information loss. So imagine that you throw a letter into the black hole, and you just follow this process. The black hole is just going to turn into this cloud of radiation, just spinning away. The letter never makes it out. So not just that, the Hawking radiation process is a local process. It happens. It comes from the vacuum near the horizon, and so it doesn't really care about the letter deep inside the black hole. It seems like it leaves almost no imprint on the Hawking radiation. Okay. Now let's just imagine, let's just suppose that the information about the letter does make it out somehow. Then you're led to the opposite extreme. There's still a problem or a challenge, which is that you get what you can call information surplus. The letters inside the black hole, that the information comes out of the black hole, it looks like the information about the letters in 2 places at the same time. It looks like there's potentially quantum cloning. Maybe somebody jumping in and collect the letter, decode the letter from the Hawking radiation, then jump in and see a copy of the letter inside the black hole. So does it lead to observable quantum cloning? That's the question. Challenge number 3 is that the entanglement between the black hole and the radiation continues to grow for the entire duration of the black hole evaporation. Here I'm plotting the red line is it's the von Neumann entropy of the Hawking radiation, because it's entangled across the horizon, and the blue line is the Bekenstein-Hawking entropy of the black hole, area of the horizon as it's evaporating and shrinking down to 0. The blue line is a measure of the total number of degrees of freedom of the black hole. What this picture is showing is that at some point, the entanglement between the radiation and the black hole is larger than the number of degrees of freedom of the black hole. That's just nonsense. That doesn't happen in a standard quantum system. If I give you a qubit, maximum von Neumann entropy you can have is just log 2. N qubits is n log 2, and that's it. This is saying that it can be black hole arbitrarily larger than the supposed size of the system.
This process, is temperature being kept constant? Is it an isothermal process?
No. Temperature, depending on the situation, if it's a black hole in flat space, the temperature of the black hole actually increases as it gets smaller,
Negative heat capacity.
because it has negative heat capacity.
But it's in thermal equilibrium.
No, no, it's not in thermal equilibrium with the radiation. Let me explain the situation that I'm.
That situation to a condensed matter person, I will have a hard time talking about entropy.
Okay, let me say a few things.
Can you repeat the question?
The question is, in the situation where you have, when you're not in thermal equilibrium, then it's hard to define entropy. Let me say a few things. First, here I'm talking about fine-grained entropy, the von Neumann entropy, the entanglement entropy. That can be defined independent of the setting. Okay. Okay, let's just give it at that then. And let me just remind you, I'm starting with, suppose you have a star. You had nothing first, just a star. It collapsed into a black hole. And then that black hole is just emitting radiation. The radiation is not coming back. Well, technically speaking, a lot of the radiation gets snapped by the potential well near the black hole and gets reflected back in. It's only the small part of the radiation that escapes. That's just a technicality I need to get into. Another question. Okay.
When you said the von Neumann entropy can't be greater than the number of degrees of freedom, is that a property of the traditional definition of entropy from the microeconomic ensemble, or is it a property of von Neumann entropy? Where does that bullet point come from?
This is a theorem you can prove in quantum mechanics. The von Neumann entropy of a system cannot be larger than the log of the dimension of the Hilbert space of that system.
And that doesn't include entanglement.
Maybe there's a terminology issue. So, okay. Here, the von Neumann entropy that I'm talking about is the von Neumann entropy of the Hawking radiation, which you can think of as the entanglement entropy between the Hawking radiation and the black hole. Am I using the terminology correctly? You can nest matter, guys?
Yeah.
Okay.
This is the entanglement entropy between the black hole inside and outside. Therefore, you cannot exceed the size of the inside.
Exactly.
So why can't it be entangled with itself at different times?
Hawking radiation? I mean, that's what you want to happen. So far, the picture that I've given you doesn't allow that. Or doesn't predict that. And hence why we're running into a problem. Okay.
Can I just get one clarity? So are you saying that, in a sense, the black hole and the Hawking radiation taken together would be a pure state? So it's a zero temperature. But if you look at each one, you trace out one of them, the other one gives an effective bath for like the Hawking radiation is an effective bath for the black hole, and I don't know if the black hole is like a bath for the Hawking radiation.
I'll say yes and no. The reason why I would say no is just that they're not a bath of the other in the sense that that they're in equilibrium. Like they're in some contact and the temperature is fixed. Not a bath in that sense. But it is correct that the combination of the two are in a pure state, that if you trace any one of them, you get a mixed state of the other.
Yes.
I would agree with.
Mixed state may not be thermal. That's what you're saying. Okay, I think I get this much.
But here, what you're finding is that the mixed state of the Hawking radiation is actually thermal all time, and it just keeps growing. The black hole has shrunk down to zero, so there's no black hole anymore. You just have radiation. You have non-zero von Neumann entropy.
Yeah, but it's not really von Neumann anymore. It's really for the Hawking part of it. It appears as a thermal stuff, right?
Here, yeah, here I literally mean you take the density matrix of the Hawking radiation and you compute negative trace rho log rho.
Right.
The statement here is that initially, at the very beginning, you only had the black hole. Von Neumann entropy of the black hole was 0. At the very the von Neumann entropy of the black hole with everything else, the entire universe, is 0. At the very end of the process, there's no black hole. There's just the radiation and the remainder of the universe. The von Neumann entropy of everything is not 0. But this seems to say that the initial state, the final state, are not related by unitary time evolution. Hence the problem. Yes?
The temperature that you showed before is the UNU temperature corresponding to the acceleration at the event horizon. Which in the UNU picture is that when you have an acceleration, you can't see past the horizon, which is I think in conventional equivalent tracing the system. As you said, right?
Yes, yes.
We'll put everything together.
Correct. Okay, so I think what everyone is getting at is the following statement. What do you expect to get if if the evaporation was a sensible evaporation? The one that followed the rules of unitary evolution. You expect something which is known as the Page curve. You expect that the entanglement entropy between the black hole and the radiation, it should grow initially, then at some point turn around and go back down to 0. It must be that the initial state is pure, the final state is also pure. Any questions about this statement? Okay.
But the initial state is not pure because it has finite temperature.
No, it is.
Black hole has it.
No, see, that temperature is like it's a coarse grained.
So it's not real temperature. That's the point.
Sorry, no, hold on. Well, we know that at the very beginning, in this case, temperature of the black hole just tells you the rate at which the black hole is going to evaporate, rate at which it's going to emit this radiation. But before it emitted anything, all you had is the black hole. And the von Neumann entropy, this rho log rho, is equal to 0. The coarse-grained entropy of the black hole, the thermodynamic entropy, is not 0, which is just a measure of the number of degrees of freedom.
So you think the initial time possible is
No.
What was the comment?
That temperature of the black hole at t equals 0, rather the mass of the black hole at t equals 0 is infinite. Because you want to, but the temperature is not equal to 0. The temperature, it's finite. It tells you the rate at which the black hole is going to start radiating.
The confusion between the thermodynamic entropy or coarse-grained entropy and von Neumann entropy.
Okay. How would you?
I think a processing black hole formation would be, imagine you have a little bottle with some gas in a big room and you open the bottle, right? The gas occupies the whole room. The entropy, coarse-grained entropy has grown, but the fine-grained entropy or von Neumann entropy is the same as the one you had before. And the temperature would also have changed, but the von Neumann entropy is still.
Can you maybe define a bit more for what is the von Neumann entropy? I guess I don't know enough about that. So.
Perhaps you can just review what the von Neumann entropy and coarse-grained entropy are for a black hole, the difference between the RT formula and
Where are we going with this? So,
I think the first statement to clarify the starting question here is that the black hole starts in a pure state. And you can define the von Neumann entropy and derive that it's 0, but I think you only need to make that statement. And the temperature is not a temperature in the thermodynamic sense. So, not in
Thermodynamically, they agreed 100 years ago and hasn't been violated. The definition of temperature is the derivative of energy with respect to energy.
Uh-huh.
And I'm not, and I think this relates to
Yes.
the statement, and that entropy does not include entanglement as
Correct.
in that definition, because that can be finite at t equals 0.
Correct. Correct. Here, that formula tells you the rate at which this black hole is going to evaporate. Just you take the thermodynamic entropy of the black hole, the Bekenstein-Hawking entropy, which is just the area over 4 g-Newton, and you just compute dE by ds. Sorry, this. Okay, and this will define for you a t. This black hole is going to evaporate according to this t.
According to this T means if you assume that it's just black body radiation at that T with that area, that's the connection. If you define, do I understand correctly what you just explained? You define the temperature as what would be the equivalent temperature of some black body object of certain area that would emit the same energy per second.
Mm-hmm.
That's how we define temperature.
Yes, it turns out that a black hole evaporates according to this temperature. Nobody disagrees with that.
At this point, perhaps we should use some
The power.
activity of the chair to ask which fraction of your presentation you prepared to ask.
Oh, how much time do I have? Okay, let me. Okay, I should keep going. I'm not going to answer that question.
Do you have wine and cheese afterwards? I would like to point out.
Okay, so again, the statement here is that it looks like the von Neumann entropy of the universe is increasing. And that's the problem. And here I'm calling it overfilling because it looks like the von Neumann entropy of the black hole is larger than its thermodynamic entropy. Okay. Now let's do sort of the same thing we did a few steps ago, which was let's just assume that there's a solution to this problem. Okay, that we know how to get page curve. Then what happens is that we fall into another pit. Let's just suppose that the entropy actually decreases after the page time, somewhere here. This would mean that at some point, the Hawking modes outside the black hole cannot be entangled with their partners behind the horizon. The only way that the entropy can go down is if this mode is entangled with the earlier radiation. Okay? If I have a qubit entangled with something else, only way I can reduce the von Neumann entropy of this qubit is to bring that something else to me. But due to the monogamy of entanglement, this precludes entanglement between this mode and its partner behind the horizon. We know that this entanglement comes from the short-range entanglement that's required for sort of having local low energy, well, local vacuum. And hence, if you break it, you don't have the local vacuum. You have some excited state near the horizon. That's the thing that we call the firewall. It looks like the state. If black hole evaporation is unitary, then you must have some sort of excitation at the horizon. These are the challenges. And any reasonable person, you might be tempted to abandon the central dogma. The upshot that past few years, something else came up. And my point to you is that you should have more faith in the miraculous power of gravity. Let's see how that happens. So first, I'm going to tell you the result, then tell you where it comes from. So it looks like it turns out that there are previously sort of overlooked effects of quantum gravity that change formula for computing the entropy of the Hawking radiation. So before, what we did was we just took radiation outside and we computed negative trace rho log rho. But what you get from quantum gravity is this messy formula, so I'll explain in a second, which tells you that the entropy is actually a competition between the original formula that we talked about and a new formula that involves the area of some surface x in the black hole and the von Neumann entropy, not of the radiation outside by itself, but the radiation, so the entropy not of the radiation by itself, but the entropy of the radiation outside, along with a region inside the black hole, which we'll call island. The way that this location x is determined, it's kind of technical, involves taking this function and extremizing it, finding the location where derivative with respect to x goes to 0. Those are just details. It turns out that because of the location of this point area here, x is really very close to the event horizon of the black hole. Notice here that I'm saying that this contribution is equal to just the area, plus dot, 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 small things which I can ignore. You justify why you can ignore them. Yeah, look at the second term. This is the von Neumann entropy of the radiation union the interior. Entropy of the radiation by itself is large. Remember, because if you look past the page time, the thing that purifies the radiation outside is all the radiation inside. So this term here is actually small, because combined state here is very close to being pure. So this is formula, and it's pretty miraculous. Let's see what formula implies. So the first thing it implies is the page curve, because remember I said it's the minimum, the von Neumann entropy, the actual von Neumann entropy of the radiation is the minimum between the Hawking answer and this new quote unquote island answer. The Hawking answer just grows as a function of time. It starts small. The island answer is given by the area of the black hole. So it starts very large and then decreases down to 0. At some point, those two cross. And you take the minimum of them, you get page curve. Okay, so this overcomes challenge number 3. Black hole is not overfilled. Von Neumann entropy as computed by this formula makes sense. Second miracle is that it gives you unitarity without requiring break the entanglement across the horizon, without necessitating a firewall. Remember, before we said you have to break this entanglement for this to be entangled with things far away to decrease the entanglement. But what happens here because of this term, it's the entanglement with the island is actually the thing that decreases the total von Neumann entropy of radiation, right? So this term is the fact that this is entangled with this, rather this is entangled with that, is the reason why this term is small. Something kind of crazy about this formula that it says that in some sense, the island should be thought of as a part of the radiation, or as a subsystem of the radiation in some sense, right? Because remember here, what I'm computing is just the entropy, Neumann entropy of the radiation far away. But what this formula tells me is that I have to involve the interior of the black hole to compute that. The interior somehow, is part of the radiation far away.
Slightly smaller than the black hole.
Is the region? Well, it depends on the situation. the region which is sometimes just smaller than the event horizon, or sometimes just outside. Let's just think of it as it's the interior of the black hole up to the event horizon. Internal surface state, I don't know what that is.
It's a volume of not surface. It's only,
What do you call it?
what do you call it?
Why do I call it island? That's, you can blame Juan for that. It's just called it an island because it was sort of the region detached from the mainland. It's just because it's just some we're interested in the radiation. And then it turns out that there's some detached region which was relevant. We just found the terminology island to be useful. That's it. There's nothing more, nothing deeper than that.
I think it's because Juan grew up knowing about the Falklands.
Okay.
The whole interior of the black hole, you say.
It's the whole interior of the black hole, yes.
So what is the difference then with the entanglement that we used to suppose before between the radiation and the interior of the black hole? So
So
what changes? Something is changing.
something is changing. I will justify why this formula is relevant in a bit. No, I'm just gonna talk about the magic of the formula.
Where in this formula is the minimization between the two curves?
Oh, good. So here I'm on this slide, I'm just talking about what happens after the page time, which means when this formula is the minimal one. Okay.
And is the island defined? I mean, presumably it's just, the way you drew it, it's sort of an internal slice in this Penrose diagram. So when the black hole stops at some large mass, say, the island takes the place of this firewall, essentially. Like, is the location of the island given by the page time?
Well, let me go back a slide. During this time here, there's no island. When you compute the entropy, it's just given by this formula. Okay. After page time, the region inside the black hole, the interior, becomes relevant. I'm just now, its relevance now is the fact that you should now there's an island.
Does radiation not go all the way up to the event horizon, and why is it at a different time than the island?
It's most likely just my drawing, but there is a precise way. There's a precise method for pinning down the location of the boundary of the island.
It's not the event horizon.
It is the event. It does turn out to be very close to the event horizon. What I'm saying is that there is a prescription for the way you find it is that you have to look for locations x, being this point, that extremize this function. That's the condition. You're asking something else.
The gap between that black dot and the start of the blue curve.
Yes, that's very important actually.
Outside of the event horizon.
Gap is outside.
Why does the radiation not go all the way up to the event horizon?
That's just my drawing.
But there's no gap.
No. Radiation is just everywhere here and just streaming out.
I think why don't you keep the nearest modes while you truncate that blue curve before getting all the way to the
Why does the blue curve touch the black ellipse?
One here.
Just go sideways from that.
You can consider that region, but let me take a step back and tell you what I'm doing here. What I want to compute is the von Neumann entropy of some subset of the radiation. Okay, I pick this point. Okay? Given this radiation region, I have a prescription that finds for me where x is, and I find it to be somewhere there. There's always a gap between them. That gap is actually going to be important.
If the hole is rotating, if the black hole is rotating, are there some directions in which the island is inside?
It's an interesting question. I haven't tried to do this for the rotating case, but actually, I think the extremization condition doesn't disallows that. That's what I suspect. Sure. I don't have anything more to say on that. Okay. Let me just say in what sense this island should be thought of as part of the radiation from a sort of a quantum information analogy. Sorry, I'm going a bit over time. This is more interesting than wine and cheese.
I'd like to suggest maybe that this conversation is going well is a reflection of the fact that the speaker is so well presenting the case. But I don't want to hold people here, so I think people are welcome to step out if they have something else to do. But otherwise, I would like to continue on for maybe 10 more minutes or 15 more minutes if people are agreeable with this. Okay? All right, so let's move on, but not like another hour.
Okay. Okay. Yeah, I guess we're definitely past the page time. Okay. So consider the following quantum circuit. Let's imagine that you have some qubits, say, and some unitary operation that scrambles these qubits. And I want to think of some subset of qubits here as the island qubits, in which I will encode some information. The statement here before the page time is that information that I've encoded, well, before the page time here is represented by the fact that most of these qubits are black hole and a minority of them are the radiation. So there's more black hole than radiation. This implies that you can decode the message from the black hole qubits. This is an example of an erasure quantum error correcting code. And this situation is represented by this spacetime, the spacetime without the island here. After the page time, what happens is that the radiation is larger than the black hole. Purely from a quantum mechanical perspective, this means that you could be able to decode the message from radiation qubits. There are more than the black hole qubits. And that's represented here by the fact that I have an island. And so this quantum picture for this process here has the analogous gravity picture where you should think of the information escaping the black hole, not by turning around and jumping out, but rather by simply falling into the island region after the page time. So this overcomes challenges number 1 and number 2. Information is part of the radiation in the sense because it's inside the island, and it doesn't need to be in 2 places at the same time. It's inside the island region. Also, you can sort of look under the hood of that unitary transformation. You can think this condition that you can decode the message from a subsystem larger than half of the qubits is something that you expect in, well, if you have a Haar random unitary, for example, but it doesn't need to be that extreme. You can consider, for example, what is called scrambling circuits. Circuits where that are composed of all-to-all interactions that happen qubits at a time. For those kinds of circuits, you expect that this property would happen, that you can decode the message from any subsystem larger than half after a time which is logarithmic in the number of qubits. This is a hallmark of a scrambling system. And amazing surprise in the black hole calculation is that, see, the function of this gap here that I talked about minutes ago is that the time it takes after which you throw in a message for the message to enter the island of the radiation here is precisely the scrambling time, beta log s, which is essentially just log n. So black holes, this is evidence that black holes behave as fast scramblers. You you can think of them. The time evolution can be realized by a circuit known as a K design. This was a prediction back in 2008 by Hayden and Preskill, that perhaps black holes have this feature. And this is proof of that. Now, the final thing is going to be, okay, so all these results are nice. But where does the formula come from? And the question I'm always asked is, what's Hawking's mistake? People love gossip. Okay, so it turns out that there are overlooked gravitational effects that lead to these new formulas. See what those effects are. Let me consider a toy picture for a black hole. Here I have space, and there's some like depression here. This is the black hole. This dotted line is the event horizon. And the cartoon of the Hawking radiation is just these two dots. And the entanglement is this, the dotted line. Okay. Let's try to measure how much randomness is in the Hawking radiation. How mixed is the quantum state of the Hawking radiation? You can do that using a so-called swap test. So the swap test, it's the following very simple observation, that if you're sampling some distribution, if the distribution is random, then sampling it multiple times would give you different answers as you keep sampling it. However, if the distribution is not random, you keep getting the same answer. So this means that if you sample it more than once and you swap two samples, whether or not the swap gives you the same answer or not can determine whether the distribution is random or not. In quantum mechanics, what you do is you consider a copy of your system, and you want to know if the Hawking radiation is random. What you do is you compare it to the state having swapped Hawking radiation. Now, the question is whether this is the same as this or not. I mean, we can all see that these are two different pictures. The entanglement lines are different. So this would seem to say that the Hawking radiation is random. However, what I just described for you here was essentially Hawking's original calculation. If you do this, you have to do this calculation a bit more carefully, and that's what led to the results of 2019. What we're doing here when we say we compare this to this, we're taking the overlap between the two. We're considering the gravity partition function starting with this state and ending with this state. In the gravity gravity path integral, many intermediate things can happen. One is that nothing happens, nothing crazy happens. That's Hawking's original answer. However, there's a small probability that during the intermediate times, the two black holes get joined by a wormhole and then get disconnected again. This wormhole at intermediate times, it happens with a very small probability. I don't know if you can read it there. E to the minus the area of the horizon. But it also has the added effect that it actually swaps the interiors of the two black holes. So you swap the Hawking radiation, and then the gravity path integral swap the interiors. Now, looking at this and this, you know, the same picture. So this tells you that with that probability there, the swap test passes. Okay. You can also do this same calculation for computing the von Neumann entropy of the radiation. Do that, you can apply the so-called replica trick. You want to compute trace rho to the n divided by 1 minus n. Because then n here means there are many copies of the system, and you have to take the overlap of the many copies with the many copies having cyclically moved the Hawking radiation. And if you do that and you account for wormholes, that's what gives you new formula. Okay? So it's wormholes in the path integral that give the new formula. And finally, this same effect can allow you, or can provide a mechanism for extracting information from the island. Suppose this is the original black hole. One way to modify the interior is to bring a copy with something else inside. So here there was one message, here there's some different message. And by bringing this other copy, the original black hole, and do some operation, which you don't want to get into the details, on the two Hawking clouds, one can enhance the probability of having these wormholes, which would swap the two interiors. Hence, you can affect the interior of the black hole by purely acting on the Hawking radiation. This is a further justification. You should think of the interior as part of the radiation. I mean, you were able to form one black hole, you can form another one. So these two black holes, A, they're not actually identical because they have different contents. B, if you can form a black hole in some quantum state psi, you know what the psi is, you can prepare another one at the same quantum state psi if you wish to do so. I mean, let me just keep going. Final thing is that there are many more arguments for the dogma, which we don't have time to go through, but this is just a list of them. Example, computing out of time correlators, the diagnosis growth of operators, chaos, and the butterfly effect. There's this very fun thing of quantum teleportation through a wormhole, which Douglas will talk about, I think, next week, or I'm not sure when, in a public talk. There's this amazing connection between black holes and random matrix theory. I believe more than one community here hears about, and so on. And there are many open problems. What are the microstates of the black hole? What is the interpretation of Bekenstein-Hawking entropy? This is more for the experts. A lot of these effects that I discussed seem to say that black hole might be dual not to a single quantum system, but an average of quantum systems. And there are many experts here that work on this. We didn't talk about the singularity going on there. And with everything in theoretical physics, once you discover a new tool, the first question is, can I apply it to cosmology? And there are some good ideas, but no breakthroughs yet. I'm essentially done. I just wanted to flash this. So Rossi already made the announcement. So this is essentially my pandemic project. I edited Joe's memoir, which he put out on the archive a few years ago. And as with everything Joe wrote, this is something that I'm sure everyone would find benefit from. So I urge you to go and purchase a copy. And let me stress that all proceeds go towards the Joseph and Dorothy Polchinski Graduate Student Fellowship in Physics. And at Santa Barbara. Okay, that's all I had. Thanks.
For the very clear, wonderful results that you got to present. In real time, if there is any, I'd like to take one burning question that is relevant to the central theme of this talk.
Thank you.
Volunteer. Maybe two, but you first.
Can one think of a thought experiment, given that now we can measure gravitational radiation? Imagine anything technically possible with that, even measuring quantum aspects of gravitational radiation. Given the ultimate thing, can one think of a thought experiment where some of this can be tested?
Well, there are many experiments that you can think of. Many experiments you can think of doing. One, for example, is just to check that the Hawking radiation follows a page curve. You can form a black hole, like the Hawking radiation, and compute the entropy. But unfortunately, well,
What would you measure?
you can try to reconstruct the density matrix of the Hawking radiation.
And measuring what?
Hawking, you can do the metrology or whatever it's called on the Hawking modes. You can do measurements in different bases or whatever. Try to reconstruct the density matrix by forming many copies of the black hole and letting them evaporate and so on. That's one thing you can do. I'm assuming infinite money, okay? So and time.
Measure intensity of radiation that will follow just simple talking. I don't need to worry about age. So.
Indeed.
May I maybe in this conversation, but Mark has never asked a question.
Never.
He should have.
I haven't in my life asked the question. Actually, I was wondering, so you mentioned earlier in the talk about the negative specific heat of flat space black holes, and conventional quantum systems typically have positive specific heat. So I wonder if you wanted to comment on whether that's in tension with the central dogma for flat space black holes, or
No, it's not intention. There's just stars have negative specific heat. If I'm not mistaken. Nobody said no. It's just a fact that gravitating systems, if I'm not mistaken, have negative specific heat.
But conventional, yeah, I guess the dogma being that non-gravitational quantum systems might describe that the black hole in the box might be replaced by a conventional quantum system without gravity.
Well, for that, consider a black hole in ADS. It has positive specific heat.
Okay. I think we should divide the question to Wang and Chi. Thank you.